Ianthosaurus hardestii was a small insectivore which lived in what is now North America 304 million years ago, during the end of the Carboniferous period. While it essentially looked like a small sail-backed lizard, it was actually a synapsid, meaning it was more closely related to mammals than to true reptiles. Early, superficially reptile-like synapsids are called pelycosaurs and were common during the end of the Carboniferous period and the start of the Permian period, but were replaced by the more mammal-like therapsids during the second half of the Permian. The other members of Ianthosaurus's branch of Synapsida, Edaphosauridae, also had sails. The namesake of the clade, the larger and more famous genus Edaphosaurus, was one of the first dedicated terrestrial plant eaters. Since Ianthosaurus is the most basal Edaphosaurid with preserved skulls, it has been critical in understanding how the early transition to herbivory happened. Ianthosaurus was named and described in 1986, but substantial remains from an adult individual were not studied until 2010. Most Ianthosaurus fossils are from the Staten Formation in Kansas. The site is close to the Iantha River, from which Ianthosaurus derives its name. Other creatures found at the Staten Formation include the predatory synapsid Haptodus garnetensis, which was medium-sized by the standards of the time, but probably still too small to pose a threat to adult Ianthosaurus. It also lived alongside Petrolacosaurus, the same early reptile that was featured in the BBC documentary Walking with Monsters. Much like Ianthosaurus, Petrolacosaurus was an insectivore. Fossils from Colorado have also been attributed to Ianthosaurus, but they are fragmentary. Even all of the Ianthosaurus specimens from Kansas are partially disarticulated, and sometimes even contain elements from other animals. But together, they account for the majority of the skeleton except for most of the tail and parts of the limbs. Adult Ianthosaurus were roughly 1 meter long. Although they were distant relatives of mammals, pelycosaurs, like Edaphosaurids, still had sprawling reptile-like limbs. Ianthosaurus's body wasn't simply a smaller version of its plant-eating cousins. Since it acquired meals by chasing insects, Ianthosaurus's neck was longer and its torso more elongate. However, its sails still would have been a hindrance in dense environments. Species of Edaphosaurus instead had barrel-shaped torsos, which contained massive guts filled with the microorganisms necessary to digest high-fiber vegetation. Their ancestors are thought to have originally acquired their gut microbiota by ingesting plant-eating insects, so the insectivorous diet of Ianthosaurus and other early Edaphosaurids was the necessary step in the evolution of herbivory. Unsurprisingly, Ianthosaurus's skull was very different from those of its larger relatives. Compared to them, it was longer, more gracile, and had weaker, shallower jaws. Unlike the derived Edaphosaurids, the back of Ianthosaurus's skull was sloped down. Due to its diet of insects, Ianthosaurus didn't need a powerful bite, and therefore didn't require as many muscle attachment points for its jaws. Its orbits were also proportionately larger. This can be partially attributed to its smaller absolute size, but good eyesight would have been a greater evolutionary priority for an insect hunter like Ianthosaurus than for sluggish plant eaters. The teeth of the Ianthosaurus holotype are small, sharp, and slightly recurved, with one tooth noticeably larger than the rest. They were well suited for processing insects and other small invertebrates, but the holotype specimen was still a juvenile when it died. The teeth found in the only adult Ianthosaurus skull are larger, blunter, and peg-like, a morphology closer to that of the more derived plant-eating Edaphosaurids. Given the partially disarticulated nature of the fossils, it is possible the adult skull actually belongs to a different species of Edaphosaurid. However, some herbivorous lizards, such as the Mexican spiny-tailed iguana, hunt insects as juveniles, so it is generally accepted that Ianthosaurus transitioned from pure insectivory to omnivory as it grew. Ianthosaurus doesn't simply represent what the Edaphosaurids were like before they became herbivores, but it is also the earliest known stage of the transition. That said, since the teeth of the omnivorous Edaphosaurid Melanetophodon were even more bulbous than those of Ianthosaurus, insects were clearly still an important component of the diet of adult Ianthosaurus. Ianthosaurus's skull also has small teeth on the palate, which could help grind up plant matter. This was the evolutionary predecessor of the tooth batteries present in the herbivorous Edaphosaurids. Their palatal teeth were larger, covered a greater area, and even extended into their lower jaws. Ianthosaurus's sail was created by heightened neural spines on the vertebrae of its back and neck. Proportionately, it was the smallest sail of any Edaphosaurid. Unlike the fellow pelycosaur Dimetrodon, who evolved its sail independently, Edaphosaurid sails have protrusions called tubercles along the spines. The tubercles are arranged together in pairs at the base of each spine, but become smaller and more irregularly spaced the higher up they are. An adult Ianthosaurus had 8 pairs of tubercles on the tallest neural spine, but unlike later Edaphosaurids, lacked any tubercles towards the end of the sail. The function of Edaphosaurid sails is still unclear. A popular hypothesis is that they were thermoregulatory devices. Early synapsids like Ianthosaurus were still ectotherms, meaning they were dependent on the external environment to maintain their body temperature. The idea is that the sail could be pointed towards the sun to warm up faster, or kept in the shade when it needed to cool down. However, the size of the sails in other Edaphosaurids makes such a function seem unlikely. Those of the largest species of Edaphosaurus are proportionally smaller than those of other species in the genus. If their sails were thermoregulatory devices, it is expected their size in relation to the rest of the body would have been much more consistent. Additionally, for heat exchange to have been quick enough to be worthwhile, the sail would have required a large blood supply. Due to its ectothermic metabolism, Ianthosaurus would have struggled to pump enough blood so high. Furthermore, the spines themselves were not heavily vascularized, so most of the supposed arteries would have had to have been located outside of the bones. This would have made Ianthosaurus vulnerable to massive blood loss from otherwise superficial damage to its sail. Rather than a tool for thermoregulation, the sails of Ianthosaurus and Edaphosaurids are now thought to have been used for display, perhaps to attract mates or intimidate rivals. They could have also played a role in protecting itself by making it look more imposing than it truly was, or foiling attempts to bite down on more vital targets, such as its neck. Since the more derived Edaphosaurid Melanetophodon predates it, Ianthosaurus was not the direct ancestor of the later true herbivores. However, it remained very similar to what their shared ancestors were like, providing a window into how the evolution of the first vertebrate herbivores happened. The differences between adult and juvenile Ianthosaurus also highlights how the progression from one niche to another is not always simple, since animals are not always limited to a single niche during their life cycle. While often overlooked, Ianthosaurus represents an important transition during the early evolution of Synapsida.
Thank you for watching, and a thank you to the Themattalorian for narrating this video. If you enjoyed it, please remember to hit the like button, and subscribe if you'd like to see more. Finally, be sure to have a great day.